I was preparing for
That's
my
fine.
speaking skills, so I was actually planning on going to Jeremiah's talk anyway. I had actually blessing.
All right.
I wanted
is
to
the camera good?
actually.
Okay. Cool. So I'm going to talk about the prize collecting network activation problem. And I'm just going to give you an overview of the ideas that were in Takeru Fukunaga's paper on it. And try and avoid the details because the details are just pages and pages of arithmetic. So what is the problem? What are bisets? What are the LPs that are related to this problem that we're going to use? There's actually quite a few. What are spiders? I do not actually have any spiders on me. This is not. And then there's a fancy potential function that's no.
So disappointing.
So that's roadmap of where we're going. So first of all, the problem has a few parts. So the first part is the network activation part, which is you're going to be putting weights on the nodes. And the weights on the nodes determine if an edge is there or not. Is the edge activated or not? So each edge will have its own function. So psi of uv is the function on the edge uv. So it's just a 0, 1 function. And this is monotone increasing.
So UV is it specifies the edge, and IJ just integers?
Those are the potential weight. Those are the weights. So it would be like I have my edge UV, or I have U and V, and then I have weight I here, weight J. Do I have this edge or not?
Right.
And when I increase J, it will never unactivate the edge, which is what you would expect to happen.
It's a monotone.
Right.
So monotone is like what the coordinate.
Right.
It's a monotone Boolean function.
Oh, but Boolean function
Boolean
usually
means
refers
that
to the input.
Input is Boolean.
Yeah. I and J can be any weights. And now, so that's the network activation problem. We're going to specifically be looking at connectivity. And there's a bunch of different...
The weights can be fractional as well or integer?
The weights can be anything, as long as the set is discrete, I think is the only, well, not even discrete.
Right.
Yeah, rational. I think basically they can be whatever you want.
But if I think of integers, I'm fine.
Yeah. So the goal of a network activation problem is to put weights on the vertices so that the edges turned on have a certain property, so that the activated edges have some property. So here, the property we'll generally be looking at is connectivity. And there's 3 types of connectivity. We can have edge connectivity or node connectivity, or what is called element connectivity. So for a given pair U and V, edge connectivity, maybe you need to have k paths between them.
Your node looks like rock.
node not rock connectivity and element connectivity. So this requires disjoint edge paths between each pair. So you can have a ton of pairs, and each pair SI-TI will have its own KI, which says I need KI edge disjoint paths. And you'll have a bunch of these, but the upper bound on these KI will be some K.
Is that a constant?
No, it's just less than n, the number of vertices in the graph. And then here, node connectivity, it's node disjoint paths. And then element connectivity is a little funny, and I actually had to read the definition a few times to understand it. So let me know if you have questions. Element connectivity is where you want paths, and they're going to be edge disjoint paths, but they also have to be node disjoint for the most part, but they can reuse other terminals. So if you have SI...
Oh, so you have like a fixed set of reusable things.
Yeah, so for example, if this was an SJ, this would be okay. So other terminals you can reuse.
So it's like Steiner node disjoint.
Yes, Steiner node disjoint would be a good way to think of it.
I mean, one question, a natural thing might just be to say, oh, I want to consider all edge and node disjoint paths. Yeah, I want to make sure that all of my paths are both edge and node disjoint.
Mm-hmm.
Now you can say, oh, that's not possible because if I have two paths going from these two vertices, then they are not node disjoint at the beginning.
Oh.
Right? But then I can say, oh, ignore those. Any other nodes had to be disjoint.
Mm-hmm.
Like you could imagine considering this. Is this considered? Do you know? That seems like a natural.
So generally when you say edge disjoint between edge disjoint paths between a pair of vertices, then it's obviously okay to reuse. When you say edge disjoint, then it's okay to reuse any nodes in there.
Yeah.
But you're saying you want...
But I mean, that's what I just said is this thing, except this thing is a little, slightly more permissive.
Yes, because so basically...
I'm just curious if it's like unreasonable or...
Can you rephrase the question then?
Let's say your element disjoint,
Mm-hmm.
except you can also not reuse any nodes that aren't like, any terminals that aren't the starting and ending terminals.
Okay, so just node disjoint paths.
Node, I mean this is node and edge disjoint.
Yeah, but node disjoint paths are naturally edge disjoint paths.
Nice.
Okay.
So like we are given like set of terminals or a set of pairs, like so instead of looking at all pairs.
What?
Like,
So you'll be given a whole set of pairs of terminals, and for any pair, I'll have a connectivity requirement between them, and you're allowed to reuse any other nodes in the terminal set. So you're not, for a given pair, you can use anyone else in the terminal set, but you're not restricting yourself to a different set of terminals for each pair. So there we go. And then the last thing about the problem we need to know is that
can we have like a combination of those as well? Like
No.
Some is disjoint and some is node disjoint?
not right now. You might be able to generalize this idea because this idea works for all of these. It's just once you start to mix and match, then you might lose some of the nice. So when you have edge disjoint edge disjoint paths that you need to build, then we're going to build these families of bisets which we need to satisfy. And we can say this family has a special property in that it is strongly laminar. And the same is true if you want node disjoint paths, but then I'm not sure if you put those two families together, if they still have the nice properties you would like them to have. All right, and then there is prize collecting. So we're just going to make this into...
So what is the original problem per se? Like you've just given us definitions.
Like the application, you mean?
No, like the problem itself would be to minimize the total weights.
Minimize the... So you want to make a graph that satisfies your constraints. So you're given a bunch of maybe edge disjoint paths constraints between pairs and how many paths you need between each pair. Now you want to put weights on the edges, weights on the nodes, so that the edges which become activated satisfy all your constraints.
Right. And how are these functions given to you?
The edge functions. It doesn't.
You just have an oracle.
Yeah, you just have an oracle, and you can look at it, and this is a discrete function. It's not really generally thought of as continuous.
So like a very special case where like each like phi is the same, it is activated when like one of the vertices gets one.
Yeah.
And then probably we want that like for every pair we just want like one path, which means that like as long as the graph is connected, we're fine. Is that like any famous problem or is
Well, the thing, if it's one, if any of them are one,
so you're like, but we want you put one vertex and we activate every edge instead of on it.
yeah, you're essentially asking like this. You can have a complete graph.
You want like a vertex, not a vertex
Or like,
cover,
yeah,
but
not vertex cover because like you only need to like connect the graph.
well, the thing is every vertex has to be next to an activated vertex. What is that called?
Dominating set or something?
Oh yeah, dominating set. Yeah. So that would be dominating set. If this was only on if I or j was at least one.
But that's not clear because like if like so one guy is connected to many guys and the other guy is connected to many guys, well like to connect these two components we need to activate one other guy to connect these two components.
Right, but if you have if you think of any edge, one of its two endpoints had to be on or not. And so any vertex that is in your connected component has to be next to a node that was activated.
Yeah, yeah, I think it's a kind of weird problem.
Yeah. Well, I think it is just dominating set. So if this is only, if you just want one path between every pair of vertices, and this is
right, but according to his example, it's not quite right because dominating set you just want every vertex to be adjacent to someone activated, but here you would want them to be connected.
oh yeah, I see. So it'd even be stronger than that. Yes, yes.
Yeah, it's a weird problem.
Yeah. All right.
The same font.
But if you want, even if you want,
and the question you might ask, like, what's the minimum weight?
like even if you want, instead of node connectivity, you want edge connectivity. You want between every pair.
Yeah.
It's sort of like minimum spanning tree.
Well, yeah, yeah, where degree is kind of weird because sometimes you're caring about the degrees and sometimes you are. Yeah.
Okay.
Yeah. Okay. So now,
so one last stupid question. What is the domain of your function? Are we going to pretend it's 0, 1?
This?
Yeah.
It's just anything. It could be
But
rational.
how could I, like, I mean, it could just be that that edge will never be activated no matter how much.
Finally, for each edge, you just need two numbers.
Like, I mean, ideally, I want to know that there is some solution, right? Like, I would like to know that there is some solution, some maximum value I can give so that.
I mean, this function can easily be specified by just like two tuples. Alpha 1, beta 1 and alpha 2, beta 2. That's it.
So-
Yeah, you
Yeah.
need a Pareto curve. How can you be two tuples?
Fast.
So-
finite or something.
Yeah.
Some assumptions would be necessary.
Yeah, I think you can assume that
Like if
every,
it has my-
all the like weights you care about are within like a polynomial range and stuff. So we're going to look at the prize collecting version of this problem. So now you'll have each pair will have a connectivity requirement and then a penalty for not satisfying it. So now we say we want to connect S and SI and TI with KI different edge, node, element, disjoint paths. But if we don't do that, then we just pay a penalty of pi I.
See, this is not prize collecting, this is punishment of It's exactly the opposite.
Okay, well, if you would like, we can punish you first and then say,
I prefer that.
say if you do this, then you'll get your prize.
Okay.
But for now, we're gonna actually think of it in the punishing of
Sadistic
way.
version of the problem.
Yes. And in this version, we're going to want to minimize the weights of the vertices and the weights and the sum here. So we're not doing it by criteria. We're just total how much we pay on the vertices plus how much we are penalized. And we want to minimize that. So are we good on what the problem statement is? Okay.
Just mention pi I out, like in case I don't satisfy the condition for this SIT.
Yeah, so you could just put in no paths between SI and TI and be like, I just pay pi I. That's what I'm going to do and just be done with it. All right. So that's the problem. And this is a small board. So now I'm going to give just a quick overview of, we can just, instead of thinking of this as this huge connectivity problem, just think of it as an augmenting problem. And that will only lose us a factor of k.
Okay.
K is an upper bound on these guys.
So we're just dealing with one pair aside.
No, we'll be dealing with all pairs, but I'm going to turn this instead of a connectivity problem to an augmenting problem. And so if we solve k of the augmenting problems, we'll get our solution that we like. Yeah.
Yeah, one question that David had. You know, if the pi i's were like tiny, then this is kind of easy. You can but somehow there's like, you have to scale them right.
I mean, the pi i's are given to you. You don't get to choose them.
Yeah, but like, I guess the pi i's have to be like a certain magnitude to be interesting. But they're not too big so that like, you know, if the pi i's are too big in terms of the wi's, then you just assign everything to be really large and then you're golden. You put huge weights on everything, you satisfy all the pi's. And if the pi's are too small, then you just assign like no weights to anything. And so there's like it's like a careful balance, I guess, even when you're given the problem.
Yeah, but that's just if you only have one pi I. Remember, you have a bunch of these floating around, so maybe I have a kind of big pi I for something, so I put in a bunch of paths between SI and TI. Then I go and look at SJ and TJ. So I put in my paths between SI and TI because the pi was on the larger side. But then SJ, TJ maybe is relatively small, but if SJ and TJ are just sitting like very close here, then I don't really have to pay that much to put them in.
Right.
So you want to remember that these pi i's are given to you in a set, and so just because one pi I is really small doesn't mean you want to completely ignore that constraint.
I guess I was curious about why it's defined this way instead of like, say, so you said that one thing you could do is that you could just, not connect anything and just take all the penalties.
Yes.
That's one thing you do. But if you said, hey, maybe I don't want to do that, maybe I want to connect at least one. you can imagine writing the kind of ratio objective or
Okay.
something. And if people do anything with that?
I don't know if people have studied
Yeah,
that.
everything is converted to dollar amounts.
Yeah, I think like
That's what.
in the real life, you can imagine the weight being like, I invest this much into a city, and only if these two cities are like invested in enough, then I put a road between them.
Yeah.
Eventually, all these costs
you're
get converted to dollars.
So you're saying
right?
that's not, you're saying it's not natural to look at the ratio. So the ratio is nice because it's sort of scale invariant.
Yeah, I guess we're saying that in the real world, you often do combine like multiple different objectives as
Yeah.
just dollars,
Mhm.
and then that's the cost that you care about at the end.
Yeah. All right. So are we good?
Yeah.
Okay, cool. So first, we're gonna just turn this into an augmenting problem. So we're gonna start with our original problem, which was this giant connectivity problem, and say, all right, we can just turn it into k instances of, we have our pairs, I don't even know what to put here, all the letters are taken. And now, I already have connectivity for all of these at, say,
K is the upper bound.
yeah, k is the upper bound of all of these in here. But the augmentation problem will say, all right, I have these pairs, and I've already put some weights on. And the weights I put on mean I have j minus 1 paths between this pair, this pair, this pair, this pair. Now I just want to augment so that they all have j paths between them. And so I'm still doing the prize collecting version, so if I ever decide someone drops out at some point, I just pay their penalty at that point and forget about them for the rest of it. So if in the second step I decide I'm not connecting S2 to T2 at that point in the augmentation problem, I just pay the penalty and move on and forget about S2, T2 for the rest of the
But you would have
problem.
already paid the first J math one and you don't care about it.
I don't care about that because all I care about is that I have these problems. The solution to each of these problems is at most the total cost of the connectivity problem. And I only need to solve k of these. So if I have an alpha approximation here, then that would give me a k alpha approximation here.
So what is the final goal? Like you want to get a K, like what will alpha be? Is it like a log or a constant?
Alpha will be n polylog. And I think it's n log squared n.
It's n log.
No, it's k, sorry. K log. K log n.
And then K is this K?
Yes. And then
So the final approximation is K squared or just K?
the final approximation, it depends on which of the connectivities you're doing. So the edge connectivity one is k log n approximation. So the edge will be k log n, and the node connectivity one will be k squared log n.
This
And-
is the final, not the alpha value. So
Right,
alpha was bigger.
these will be, the alpha will be a log n, and a k log n.
I don't know about elements. I mean, it's such a weird thing. I probably never would care about it.
It's not in the, oh wait, element is also k squared log n.
Sorry, why in this sort of reduction here do you multiply by k? I think I missed something.
So I'm gonna solve k augmentation problems.
Yes.
So each time I'm gonna increase the connectivity between my pairs.
Yep.
by 1, and I need to solve this k times.
Yes.
So I'm not going to do anything fancy. I'm just going to start solving. I'm going to solve it for the first case, so I have to go from no connectivity to 1, and then 1 to 2. And I'm just saying each of these k augmentation problems, each of those augmentation problems has a solution which is at most the cost of the connectivity solution. Because if you take the connectivity solution, then obviously it also satisfies, it's a valid solution to your current augmentation problem. So I'm just doing something really stupid here. I'm just saying, all right, I want this to be a little easier. I'm just going to look at augmentation. I'm going to have to solve k augmentation problems instead of solving one connectivity problem.
Also, my point, I guess, like, so you only consider those pairs from j minus 1 to j, the ones who have the requirement of j. The ones which have the requirement of just j minus 1,
you'll just forget about them.
Yeah.
Yeah. Okay. Nothing fancy. Just we're going to work on the augmentation problem from this point on.
Can I ask one more question?
Yes.
If I wanted to, if k was like really big, are there any known results where you get a sublinear dependence on k?
If k were really big,
Like maybe, I don't know, n goes from log n to log squared n, something terrible like that, but k is like k to the 0.9.
I don't know. Normally when I think of k as like some constant, which is like 100 or like 3
that's probably
or
more,
something.
yeah, more reasonable. I'm just wondering if there's anything that kind of gets around this sort of construction.
Right, because if you have something that's linear and you don't have like the prize collecting version, so if you need n paths between everything, you're basically putting in a pretty dense graph. So that's a very...
Yeah, but even if I ask for like your k is like polylog n or something, then it's...
Yeah.
Also, this paper defines the problem, or the problem was defined before?
The problem was the prize collecting network activation problem has been defined and studied before, yes.
What's the hardness?
What is the hardest?
Of course you would ask that.
That was not something I was thinking about before this talk.
Yeah, don't worry, if there's no hardness yet, there will be one. Yeah.
Well, I think you could just do like a stupid like set cover hardness sort of thing. Probably. You might need to make it a little more complicated, but I think you can just have kind of a bipartite graph and the edges will only care about one side of the weights. So that's that is a good question though. Okay. So working on augmentation problems, good. Probably set cover hardness.
We should get a student cut out with a speech bubble that says one summer. Yeah, just bring that to talk.
So I'm going to define what a biset is, finally.
You're 40 minutes in, so I'm fairly certain we're lacking potential.
As long as we get the
I want to get
spiders.
spiders.
That's what I came for.
Here for spiders.
Okay, so what is a biset? A biset is an ordered pair of two sets.
Okay, moving on.
So he doesn't matter, we got LPs now?
Not quite. So I'm going to have to define a little bit of terminology. So x hat represents the biset, and then you have x and, is it just, oh, it's x plus, that's what it is. And x is always contained in x plus. So this is x here, and this is x plus. And Then a couple more definitions which are useful. These nodes which are in here are what are called the boundary of the biset x hat. And then we have edges which go from completely outside of the set to the innermost part. And these are delta. If you want to say which edges you're picking from, you put them down there. And these will be directed eventually from going out of the sets. We'll be thinking of directed edges, but that only loses us a factor of 2, which we don't care about at this point. So these are going to be directed edges coming out of the sets. So these are the things we care about. The bisets are x, x plus, the boundary, and then the edges which go all the way from inside the biset to completely outside the biset.
And what was the subscript of delta?
If you have a particular edge set you care about, which we will sometimes be looking at. So instead of looking at all the edges, we might restrict ourselves to only looking at some of the edges.
Okay. And these x's are, of course, like a subset of the vertices? So.
Yes, both of these are subsets of the vertices. And now these are useful because these will help us with our augmentation problem. We'll have a family of these so that if we cross, these edges are called crossing edges. The delta of x hats are the crossing edges. If we cross every biset in our family, then we'll be able to augment and satisfy a given constraint. So if we are looking at our particular type of connectivity, we're going to define VI edge. So this is a family of bisets, and this is just denoting that we're working with edge connectivity here. So that we have X that is going to contain our SI, and out here will be our TI. And then of the edges we've currently used, so the edges which we've already used in our augmenting here, which will be called E naught. So here's your example where you're only looking at a subset. So we only care about the edges we already put in, where this edge set has size exactly k minus 1. So this family is all such x, x hat which satisfy these properties.
So, but I mean, x plus is just any superset of x.
Yes.
Okay.
And so we care about
Any superset where the edges go from S to outside.
where the edges, the number of edges going from SI to outside is exactly k minus 1. So now, I'll argue if you, if you have this family and every biset is crossed in this family with a new, so you'll be putting in new edges. If the new edges you put in cross every biset in this family, then you've just augmented. And now you have an additional edge disjoint path from SI to TI.
Sorry, what was crossing?
Crossing is going from the center here to out here. So we already knew that we started with k minus 1 guys, going from in here to out here.
Even if the connectivity is k minus 1, there might be like x hat with this number less than k minus 1. No?
It will if Ti is inside x plus.
Even if it's not the case, probably like So X to just about just right outside, but like they have a.
Yeah, there could be like one node
Yeah,
where
there's
like
like
they're
no,
k
like,
minus
jumping
1 and then they
back,
all
like, they're
connect to the same
somehow,
thing. Like,
Oh,
yeah, you could
I
have the k minus
see.
1
Oh, wait.
nodes on the outside and then there's one edge connection to that. So if you-
I didn't read this one right.
It's like nothing. Maybe one left.
Yes. This is the uninteresting one because x has to equal x plus. So yes,
Okay.
you're right. So in this case, x has to equal x plus.
Okay.
And then we'll have another family for the nodes.
And here I just means at the ith step of your process.
Yeah, so
Yeah, like
So-
Ith augmentation step.
so this will actually be I minus 1. Oh, no, I here means SITI, sorry.
Oh, yeah, you're right, you're right.
Yes.
why don't you use, I guess since we're just doing normal augmentation, but you could use like k at minus 1 there? Or, anyways.
Yeah, why is it k minus 1? It should be I minus 1 then.
No, I minus 1 is
No.
the pair.
Oh, okay.
I-
No, I was thinking like k sub I minus 1.
Okay.
I guess we're just tolerating our expected k loss.
Oh, I see. So we're going, k is the current iteration.
Yeah.
It's not the max anymore.
Yeah. So now here,
Oh, okay, yeah, that makes sense.
we look at the edges which cross and the number in here. So we want the number of things in our boundary. Plus the number of edges going across to be at most k minus 1. And if we augment here, then we'll also be good. So, yeah.
Just to understand, you're saying we have two different scenarios where we're considering one is the edge version, one is the node version. In scenario 1, we look at the top thing, and in scenario 2, we look at the bottom thing.
Yes, so scenario 1, we're going to be making this family of bisets, and in the second one, we'll be looking at this family of
Yeah,
bisets.
so in scenario 1, we say, what I'm looking for is a set containing all the SIs, but not any of the TIs.
No. SITA is one pair.
Yeah, sorry.
Yeah.
For each I look for a set containing SI, but not TI. And then I want it to be the case that then I already have some edges that have been activated, and I want the number of edges that go from inside of that set to outside of that set to be exactly k minus 1.
Right.
And now you're saying, given a family of such sets, if you augment it, then you automatically get k.
Right.
And is augment like the thing that I learned in undergrad algorithms that like should work, or is there some other procedure that you're gonna tell us?
We're just gonna add edges, and if the set of for every set there's an edge in that crosses. For every biset, if there's an edge that crosses it, then we're good.
So basically, the first thing is just like look at all the sets that don't have k.
At least k crossing them
great.
already.
Okay.
And how are you guaranteed that, is this I guess a proof that you have to do later, or is it obvious that I'm missing it? Well, how are you guaranteed that it will make your graph k
Because it's true,
connected?
it must be true for if it's true for every possible set, then it must be like.
Oh, this is every possible.
Yes, so
Got
this
it.
is every set that satisfies this. So we know every other set, since there's k minus 1 connectivity between them, has this, greater than or equal to.
Right.
But we only need to worry about going from k minus 1 to k, so we only focus on those that will prevent us from getting to k. And so the same thing is happening here. We look at the number of edges that go across here plus the number of nodes here, because we care about node disjoint paths. And this is equal to k minus 1.
But how did x equals x plus? What did that mean?
This is for this case. So in this case, x and x plus are the same. So your biset is kind of silly. Your biset is actually, looks like that. You're not going to have, your two sets are the same.
The two sets x equals x plus.
Yeah, it is in the edge connected case bisets.
For some reason, she only needs these families. She won't need
And in the top case,
So I need those for the node.
for each of those edges, there's just going to be some clever way to add an edge.
Yeah, so the spiders are the edges I'm going to add.
Okay.
And I'm going to say that all those edges with which I'm adding don't have too much cost, and they cross all my bisets.
Okay.
And this family of sets will have like some nice property of laminarity or something.
Yeah, like linearity, I mean, and other nice properties. They're what we call, this first set is what we call uncrossable, which is what you kind of would expect. So if, yeah.
So in this bottom one, what I should think of as being in the boundary is being like the different sets. I guess there are now K-1 edge disjoint paths from SI to TI, right?
Right.
And so now what I should think of as including in this boundary set is like the different vertices from those disjoint paths.
Right.
Okay.
So these, I mean, these are some of the vertices in the node disjoint paths, and then you're also going to have the other node disjoint paths which might jump across this.
And it's slightly, maybe a little less obvious why ensuring that you add another edge here will get you one extra connectivity for all of the vertices, but you're just saying it's true.
Yeah,
Okay.
it's the same idea here. It's just if you get into the details, it's a little less nice.
Okay.
So now, I guess I'll tell you what uncrossing is. There's also a family for the element case, which I can go through, but I'm trying to keep going. So uncrossing means if you have our uncrossable family V, then if you have two bisets in your family, then either their union and their intersection is in the family. And I'll define these. Or their differences are in the family. So the unions are what you would expect. So you would union the first guys and then union the second guys. And the same goes for intersection. Difference is a little more complicated. So if we take x difference y, we take x without y plus, and then we take x plus without y. And so basically, we know the family of all, so if we take all of the VI edges, then we know that that family is uncrossable. So it's not just one VI, but the union of all the VI edges, that is an uncrossable family.
So union over all I.
What?
You're not saying like not just for a single I, but like
Right. So I say
union over all I.
union I of this. I don't even have to throw anything else in. Then this is uncrossable.
It's sort of like just the shortest path.
Yeah.
What?
I do union over I over?
Because they're never gonna, if they cross, you could just uncross them.
It's like when you're doing min cost flow, max cut, max flow min cut, and you look at the dual and you do the uncrossing. It's the same sort of idea there, where your tight sets form this uncrossable family, except we're now saying our tight bisets, or the bisets we care about, form this uncrossable family.
So if I can just imagine it. So okay, so I union together all these sets. If I took one set that contains SI and then like another set that contains SI that both have this property but they're very disjoint, couldn't it be that when I union them together, they'll just get a bigger set Could it be that it has more edges going out?
Could be.
But
But it
that's
won't.
not saying, that's just saying they can be uncrossed. It's not
One
saying-
of these two is true. So either both of these are in the set or both of these are in the set.
Okay, so in that case, probably the union would not be in the set. The difference wouldn't be in the set either way.
I mean, I can go through the casework. I'm just gonna go through it. But basically, you can check if you have two such sets. It's the same idea as if this set has k edges crossing it, and this set has k edges crossing it. So when you're doing min flow, max flow, min cut, then you also know, if you know your min cut has size at least k, this thing has at least k things crossing it. This thing has at least k things crossing it. And if they both don't have at least k things crossing them, then you have a problem, because you only have k things here and k things here. We have a similar sort of thing here. We actually have the same thing because we're not working with sets, we're working with bisets. Every set is crossed to the extent at least k minus 1.
So it's if we define this family to be at least k minus 1, but not equal to k. It doesn't work with
Every set is crossed that goes from SI, that disconnects SI from TI, has at least k minus thing once crossing it. And we only, yeah.
Yeah, I guess I could believe something like this.
Okay.
I guess in edge version, probably not even the or x minus y, y minus x is not needed. In
I think
edge
it's,
version, just one, we have just one set and we can just cross.
it's not,
Yeah, I'm not clear.
So is this true for VI nodes as well?
No. Okay. So we're going to look at the LPs now, and there's quite a few of those. Are we good with bisets? I want to try and keep moving so we can at least get to spiders. The potential function isn't that interesting. So.
I think we're setting expectations pretty high with these spiders.
Yeah, I think it'll just gonna be a letdown. Not that great. Okay. So, just the natural OP you might write down is where you sum over V and V, and J is in W. So W is just the set of possible weights. So does vertex V get weight J? And then are we going to satisfy constraint Y? So now we need to see if the constraint is satisfied. Do we satisfy constraint I? Or do we pay the penalty for it? So,
Are you laughing? Oh,
what?
I thought you were laughing. That made me laugh.
So here A is just the arcs that we can activate. And here, this is psi of UV. So this is just saying the set of J prime such that UV is activated.
Sorry, what is W?
W is just the possible weights.
I see. So you do want your weights to be discrete.
Yeah.
Yeah.
Okay.
This is not in the sum. So this is at least one. So either you have an edge which is activated and crossing the set for all bisets x star in VI and all I.
So that's either VI edge or VI down?
What?
Like the VI there, that could be either VI edge or VI down? Or?
Yeah. And then from here on out, we're not going to worry about edge or node or elements. We'll just worry about the families of bisets. Next, you try. Here also the edges are directed. As I mentioned before, we only care about edges that go out of x into the part that is not x. This is okay, it only loses a factor of 2. And then all the non-negativity constraints.
So you do want x, u, v, j, j prime is equal to, like at some point you need to use your threshold function.
That's like included in the psi UV.
This is the psi UV. So
Okay.
is that edge actually on? Well, if it's not on with those weights, I just don't include it in the sum. So
Let me be an idiot here and go through everything. The delta of A was when you had the x and the x plus, and it was the set of edges contained in A that went from x to outside.
yes.
Okay. And xuv is a variable in the.
Yes. Yeah.
And.
Well, it's x.
And it's just one. It's supposed to be one if on edge uv the value of u is j and the value of v is j prime.
Yep.
Exactly equal to, or like at least.
Exactly equal to.
Okay.
Because it never has, this never has any reason to be more than 1, because we are looking at a sum. And everything's non-negative. And these,
I guess we're minimizing.
yeah, you're minimizing the sum of these. So these never have any reason to be greater than 1. These never have any reason to be greater than 1.
If you don't have any like price collecting parts, we just need to like ensure every connectivity that is the problem getting. Yeah, so if you just look at the like original problem, then is it easier? Is it to approximate or is it the same?
The non-prize collecting does have better approximation. The non-prize collecting does have better approximations. So for non-prize collecting, you can do a factor of 2 if you're doing, but that's not for network activated though. So if you're just building your network and you're just paying for edges, you're not doing this network activation thing, then you can do a factor of 2 for non-prize collecting. But when you're doing network activation, nothing, this is actually the first paper that does it for network activation for non-prize collecting also.
So approximation the problem is a level network design? That's the problem?
That's a generalized standard.
Yeah.
And I know you already answered this question, but one more time, the psi or phi or chi or whatever you sub uv.
This is just the weights that turn edge UV on.
Okay.
Is edge UV possibly there with those weights?
Yeah, it's the inverse of that open function you defined earlier.
Kind of, yeah.
Inverse of what?
The weight function, or the
It-
activation function.
Yeah, you
Yeah,
can
yeah.
think of it as
Yeah.
little psi UV inverse 1. Yeah.
That's the set, yes, the set.
And these are,
Sorry, can you remind me the monotonicity thing said that like it increases with j plus j prime? Or does it increase with j like the
No.
partial order?
It just so when If you increase j, then it can only increase. If you increase j prime, it can only increase. But
So it's like the partial, yeah.
And this is, A here is the set of edges which have not been activated yet?
Yes. So the edges which have been activated, you can't use them again.
Yeah, exactly.
Where is like the current value of x if there's any, or that's not given?
This is thrown out when we did the augmentation problem. We're just paying for it k times. We're just being very silly. This is just like the first approximation for the network activation problem. So I don't care what. I can update them if I want, but at this point, even updating them, I don't have a good way to keep track if I updated them of whether or not that would actually help me in my approximation. So right now, yeah, you can just pretend that we're just ignoring whatever we already put on the vertices, which is kind of silly. But.
And the VI could possibly be like exponential size, but this is, you get it? Or?
Yes.
But this is one of those things where like you solve it by some method that makes it not a problem.
Right.
Okay.
This actually isn't even the LP we're going to use. This is just much easier to look at than the first LP.
Okay.
There's 4 LPs.
Oh my god.
Where do you keep to account the number of tabs you're trying to get?
We're only augmenting.
You're only augmenting.
So all I care about, so I already have some edges I turned on, and I'm just ignoring those. Those are already taken care of by the definition of what my family.
Oh, because you already have like the J-minus one and the K-minus one in there.
Yeah. So when I made my families, I looked at the edges I needed, and we argued once we have edges that crosses every set in that family, then we're good. So implicitly, they're swallowed up by the bisets. Okay.
Let's see some more LPs.
Okay, so this LP sucks.
I like it.
No, it has an integrality gap of m, the number of edges.
Oh my god. Erase it. Yeah.
I'm sorry. Okay, so now we're going to fix it a little bit, but I wanted to start here because it's a little more comfortable. So I'm going to keep this. This looks nice. So now I'm going to change this. I'm going to put a C hat in here. Yes, this is a C hat. And this is for all X, and this is for all C hat, so that it's kind of contained in X hat. So C hat, what we care about is that it's a min core. So V is the min cores. And what does this mean? It just means take all of the bisets in V, which don't have anything smaller than them in V. There's nothing that is contained within them. So you just take all the smallest stuff, and those are your min cores.
So these form like, are these disjoint? No.
Yes.
They are?
Yes, because the families we're working with is uncrossable.
Right.
What do you mean by disjoint? Like don't like all the like there's C and C plus. Doesn't C always contain SI? If we're looking at VI.
So.
Might be listening again.
So the thing is, there's multiple cores in the family. So there could be a core. This is a core in the whole family. So this could be a core that corresponds to separating SJ from TJ. So you, as a biset, could contain a core which separates SJ from TJ and a core that separates SI from TI.
I see. So yeah. Oh, so V. So that yeah. You specifically mean M sub V or not? That's not like forgetting the I or anything.
Right.
That's,
Yeah.
We're looking at all the UV. Gotcha.
Yeah. Okay. So then we're also going to have to do a little bit of work here.
You can add C hats to everything.
Yes, I'm going to add C hats to everything, but to do that, I am going to have to move this over because I also need to add a summation.
Was it obvious why the original thing would have like a terrible inequality with that? Like, is there another LP
There's
that's similar to
a
it?
specific
Like
instance, yeah. I can go through.
Probably we don't have enough time, but
Yeah.
I'm just wondering, like, it kind of looks like people are saying, oh, it looks maybe, or maybe you said it looks somehow like the flow LP or the max flow.
So the main way to think about it is think of a edge, which is similar to what Yuan said before, which is on if one of its edges has weight at least 1.
Mhm.
So the thing is, in this LP, say you had something that was very similar to a star, and all those edges, so you have M edges. Now let's say I just put weight 1 over M on U getting weight 1. But then all of its edges get turned on to the extent 1 over M. But 1 over M times 1 is 1, so it crosses a set. But then my cost up here is 1 times 1 over M plus nothing else, so it's just 1 over M. But to have any edge on, I need to pay at least 1. And we can pretend our penalties are huge.
Okay.
So that has a cap of them.
Okay. Cool.
And now we have we're gonna sum over U, V, and A. We're gonna sum over V, and then we're also going to sum over just valid J primes. So J, J prime, and our weights. And then we're also going to have to add the C, like you said. And this is for all UV, this is for all U, C, hat, oh wow, this is actually X star, X hat, I missed something up over there, and J. So this is V is in X. And then you do a similar constraint here where there's also C hat here. So what is this constraint saying? This constraint is saying if I put weight J on U, then the edges which go from U out of V, from U into X, so 2V, then the total weight on those guys can be all these edges and all these weights. I have to distribute my weight from UJ from. But I can also specify a core set that it corresponds to. So not summing over the core sets, the C hat. And this is to avoid using a little bit of weight, something weighted a little bit to completely cross a biset X hat. So if a biset x hat, this is also with c hat within x star. Basically, it's saying for each core I have and each set x hat that I cross, I can only have so much edge that I actually use. So I can't use a bunch of different edges a little bit to get me entirely crossing a core, even if I only pay a little bit.
This is summation. Never mind.
It's a sum over
Yeah, I got it.
v and a sum over the other possible things, the other possible
I
costs.
see. So you just look at like literally every single neighbor you have.
Every neighbor you have so this is going to be for every x hat. So for every x hat and c hat, you do this. And you look at all the things which go from u to v in x. And all the possible costs j prime that you can put on it.
I don't know. I would think that if I look at every v that I'm adjacent to,
It's not every v. It's every v that's within a
yeah,
particular
that's within.
biset.
But you can imagine multiple of them. So x, u, v, j, j prime just indicates that u gets j and v gets j prime, right? And that this and
This indicates that u gets j. This indicates that uv has j on one side, j prime on the
yeah,
other.
and furthermore, that thing satisfies.
This set helps out bisets that contain c hat.
Yeah, and I'm wondering why, like, would you not expect, since the left-hand side is an indicator random variable, or indicator variable in a good solution, and the right-hand side is a sum of indicator variables, that, like, maybe I have a one for, you know, uv, and I have another one for uv prime.
So what it turns out is
Oh, maybe,
that
you're only trying to find one.
you don't have to have, just because you have a solution where u gets cos j and v gets cos j prime, does it mean all of these have to be one? Also keep in mind, this has the c hat, and we're not summing over c hat.
Right. Yeah, I guess I'm concerned about the summing over the b's, but I guess you're saying that not all of them have to be one,
Right, I just
even if they
need,
kind of should be.
I just need only one of them which goes into x. So it's basically, I have a solution and I have my bisets, and for each biset I kind of choose a representative edge.
Okay.
And so this is an LP which is a mess and is awful, but it is separable. If your biset family is uncrossable or has other nice properties
What do you mean separable?
You can solve it.
in
You
polytime.
just test the things feasible.
You can use the ellipsoid method on it.
Is that like a technical term that everyone knows with me?
I think that.
You? Yeah, okay, cool.
Okay. And then there's the simple LP, which is simpler than this, and which I will write up there. What's interesting, and I think is the really cool part about this paper, since I only have 10 minutes left, is this is the LP they solved to start. And the only thing they do with this is they round their yi's. So they solve this, that's like, they can do that, and then they round their yi's up if they have value at least a half, and then round them down otherwise. So this is another constant factor of 2, big deal. And then they just they commit themselves to, all right, if I set y to 0, I have to satisfy the constraint. So they use the simple LP. This simple LP does not solve the problem. The simple LP, feasible solutions to the problem are not necessarily feasible for the simple LP. They use the simple LP and they solve multiple, they look at multiple iterations of it and build spiders at many different points. And they just relate this cost of the simple LP to this complicated LP.
The simple LP was the one which you wrote earlier.
The simple LP to this one.
Yeah.
Because we don't want to use the one we wrote out earlier. And so that's the really cool thing, is they have this LP, which doesn't work for the problem, but which they use to actually bound how well they do in finding the spiders. And so they'll, on the simple LP, they'll do the primal dual method to find the spiders, and then they say, all right, the simple LP has cost in a bound related to this LP, factor of 2 away. And then and then that's how they bound it.
No.
No?
You have not written the simple LP.
I haven't written the simple LP. I'm going to write the simple LP. I just wanted to say what the cool idea was before I ran out of time. So simple LP. Simple LP is going to explicitly direct the edges. So this is kind of silly. So we're saying, do the in edges of V have weight J on one side, and then this is an indicator variable for the out edges of V seeing weight J on V. So it's kind of a little funny. So this is the same thing we looked at before, edges crossing the biset, which are actually activated. And then so now we drop the stuff with the cores, and this looks very similar to our original LP. I'm not gonna write this junk again, but it looks the same, except we're summing over U, which are completely outside of the biset. And this is for all bisets, and this is for all bisets.
You mean you were summing over V outside? Or in
this is a V here, so we're summing
over
over U here. And then J's and weights. So this is the simple LP. And it turns out all we're going to do for the simple LP is have a family of bisets which is strongly laminar, which is a stronger constraint than being uncrossable. And the family that we're going to use here, we're going to update at multiple steps. So we'll do a primal dual, but we'll be changing the dual, but then we're also going to be changing the LP that we work with. And as long as this family has nice properties and is a subset of the original family, then this turns out to all work out nicely.
Do you know the running time of this algorithm? If you put everything together.
Polynomial, yes.
You know what I mean?
Uh,
I'm just curious if it's like, if it's, you have like so many for loops and solving LPs every step and updating LPs with other LPs.
so I think the hardest part is the separability of the first LP.
Mm-hmm.
So you have to run the ellipsoid method, which I don't know what on its own it takes, but then also the separability oracle takes like n cubed time. So you'd have like a n cubed times n to the 6th. So at least an n to the 9th running time.
Not too bad. As long as that is more than 2.
So I think I'll stop here because,
You could give the definition of spider.
Yeah, I want to know,
Okay.
or like a picture of a spider.
okay.
Can you draw a spider?
Yeah.
If it just draws a spider with 8 lines,
So,
it's 8, right?
It is, yeah.
so,
You have a centipede.
Yeah, I wasn't sure if it was 9 or 8.
Yeah.
But then I was like, 9, it's
That's
probably.
actually interesting. Just one little.
That's all.
Yeah, was that the odd number of like?
Yeah.
I think centipede isn't actually 100, I think.
No,
Yeah, but it has an even
no,
number.
but it's still even.
Are there any animals with just one leg? Because that would be
Plants
nice.
have that one little arm.
Oh, true. They have a pseudopod, I think it's called, right? It's not real life. Yeah. Anyway, sorry.
it's okay.
That's too long. Or odd stuff.
I don't know what a good way to draw this is. Because I don't think these spiders look like spiders you're used to. Because most spiders that people think of look like this, right? No, like in the graph theory sense. Like this is a spider.
Yes.
This is the head of the spider and these are the feet.
I've never tried of spiders thinking graph theory sense before. Do you ever see a real spider walking around? It's like, that's not what a spider looks like. You're not a spider with a graph
So this is typically what a spider looks like, which is where you have a head which has a large degree, large being 1 or more, and everything else has degree 2 or 1. And the 1 degree vertices are called feet. So that's what a spider is generally in the graph series sense. In this sense, it's interesting because we only really care about bisets, so this might not be connected. But every vertex besides the head will have degree at most 2. So if you have some nested families of bisets, so it's hard to draw bisets because they're like 2 sets, but here's a biset within another biset. Then maybe you have an edge which crosses here, which crosses this set. And then another edge here which crosses this set. And maybe here's the head of your spider, and this goes somewhere else to help with other bisets. And so there's some other bisets going on here, and some other bisets here. But basically, you have sets of edges which will cover all your families, a certain family of bisets. So the spider, all of so this edge covers this biset, this edge covers this biset, this edge should cover some biset or it shouldn't be there. But this is a spider because it has 1 high degree node, everyone else has low degree, and it nicely covers some. And notice here that these are all nested, these are all nested, and these are all nested. So the spider here is going to cover a nested family of bisets here, a different nested family of bisets here, and a different family of nested bisets.
No. So you'd hope that you slap down the spider and it creates everything connected, but like obviously some of these things are not connected. So then do you have to do like multiple? Is this why you need the multiple spiders to like connect this thing in the?
No, you don't need to connect these because we just need to cover the bisets. If we cover the bisets, then we're good.
Yeah, you're guaranteeing that there's now 1 edge coming out of each of them.
Yeah.
And then this magically connects them all.
Right. So it turns out you can bound the weight of this spider by doing primal dual. But the thing is, this spider doesn't cover everything. But then it just becomes a set cover thing, which is saying, all right, so
And that's where you get the login.
the weight of the thing I bounded divided by the number of nested families I get is at most the cost of the LP that's associated with this family over something else. Don't worry about this, actually. It looks like this. And so what we're actually doing is finding minimum ratio spiders and adding them. And since we're finding minimum ratio spiders, we're just doing set cover.
And that's where you get the login.
That's where you get the login. Yep.
Cool. Let's find
So then is login a lower bound for this problem? Just because it's set cover?
I think that was the idea I kind of suggested to you when he asked for hardness, was that I think it's closely related. You can find an instance of set cover hiding in it easily.
So
Yeah, I mean, a login lower bound would be, now we think K is a constant.
even if it's one SI together pair, is it like, is this hard? Is this easy? Like, I think I can solve it if it's like very special cases, but
Can you?
I think if it's like, if your graph is a tree, then yes.
Oh, okay.
I can solve it on n equals 2.
Right, but this is
obvious.
but
I
no,
mean,
no.
it took me a while to think about it.
Guru, how would you do it for the network activation problem though? Because you have to put the weights on the vertices. So even deciding what weights to put on, because it's not.
No, but you can do it on a path if it's like dynamic programming.
Oh, I see. Yeah, you could do dynamic programming.
And that's how I did it. But then I was like, wait, how on earth am I going to do it on a general graph? I can do it on bounded tree width because it generalizes, but
Interesting.
One path.
like one path, like you can do DP and you can get it.
I mean, yeah.
But can you do it like in a,
General graph like case one,
yeah, how do you do it?
you only need one path. You find people.
Can you do something? I feel like maybe there's some weirdo generalization of what's that one guy's, the A star algorithm, or who's the Dijkstra's algorithm that like.
Yeah, but I mean, even if you have two paths, it's not obvious.
Well, I'm not asking for 2 paths. I'm asking for 1 path.
No, I think your graph is just two paths. SITI,
Oh.
and then there's two things.
No, but I'm throwing out things that maybe some idea like this will work.
A star?
Yeah, A star or.
But how do you do A star on this? What does that even mean?
Yeah, A star you like expand your set.
Yeah, but you need like a heuristic. I should know this at my A exam on Monday.
No, but like if you have A star, right? Then you're like you need to assign weights to the vertices so that there's a connected path.
Right.
Right? So what is the set that you're growing?
Your set of vertices. Wait, are we looking at a complete graph?
Sure, why not? Because,
Yeah,
but
why not?
because
Just
the,
have like arbitrarily large, like.
Yeah, I
Yeah.
imagine you would, I feel like you do some sort of like queue where the vertices I want to consider first are those that correspond to like having lowest weight necessary.
I see. But the thing is, it's bipodal. Like it could be that so I can construct a case where the right answer is just like there's one special vertex and you assign it a very high value, and when you do that, everyone adjacent to him becomes activated.
Yeah.
And so I can connect to anyone.
But I mean, essentially, what I want to look at is like, consider all paths of a certain. I'm thinking like, consider all paths that have a certain amount of weight total.
Yeah.
Maybe of length 10. And now one of these